Section 2.7, Linear Inequalities and Absolute Value Inequalities. To begin with, we want to introduce interval notation and set builder notation to indicate sets of numbers, and specifically here, all real numbers greater than or equal to -2. Before I do either of those, I want to draw a number line. All numbers greater than or equal to -2 can be indicated by drawing an open circle here, including this, and shading everything to the right of -2. So set builder notation is exactly what you read. Okay, this is x. So I can draw one better than that. Okay, x such that x is greater than or equal to -2. That is set builder notation. It's literally a listing of how to determine what numbers fit. It's the x values such that they are greater than or equal to -2. Numbers that make that statement true. That is set builder notation. Now, interval notation is better seen from the number line because we're going to indicate this by -2 to infinity. -2 to infinity. My left endpoint of that set of numbers is -2, and also it's included. Notice the bracket there. Okay, so a bracket means that number is included. Parentheses means not included. Okay, that's the meaning there. For instance, in this case, infinity is not included because we cannot actually reach infinity. We can head towards infinity. But we cannot actually arrive there. Okay, so an interval notation and set builder notation. Now, number 2, write the interval expressing all real numbers less than or equal to -1 or greater than or equal to 1. All right, well, I'm going to draw a graph for that again. Numbers that are less than or equal to -1, there's -1, okay, less than or equal to, or equal or greater than or equal to 1. Okay, so or greater than or equal to 1. All right, well, if I were going to write this in interval notation, I would start from the left and I would say -infinity up to -1, and I am including it, so I'll put a bracket there. But then I've also got this separate interval, which is at 1, including 1, going to infinity, not including infinity. The way I'm going to put these together is something called the union, okay, a U. Effectively, it means put the two together. It's the glue when it comes to intervals. We will need that in lots of places. All right, now illustrate the addition property for inequalities by solving each of the following. Okay, and that should be a +4. Let's scratch that. All right, so to solve this inequality, I'm going to add 15 to both sides. So that would be x is less than 19. X is less than 19. So the way that I want to indicate my answer is I could actually type or write x is less than 19, or I can write less than 19, which means my upper limit is 19, and my lower limit is -infinity. Not including -infinity, and not including 19 as well, because I don't have less than or equal to. Okay, so this indicates everything strictly less than 19, so 19 is not included. All right, part B, we'll add 1 to both sides here. So I have 7 is greater than or equal to x. A better way to see what I'm working with is to write that as x is less than or equal to 7, which will be very similar to that last one, except that 7 is included. Note the difference between those two. All right, part C, subtracting 7, x is greater than 2. So greater than 2 means we're starting at 2 and going to the right. So starting at 2, going to the right to infinity, and we do not include 2. So up to this point, inequalities work exactly as equations do. The place where things change is when we multiply and divide. And the only way that it changes is if we multiply or divide by a negative. Okay, so let's consider this example off to the side. If I have the number line, okay, here is 0. Say here's 3 and here's negative 3. There is somewhat of a reflection going on here. Okay, what I like to call the reflective nature, okay, of the number line. Reflective nature. Because if I take, let's use a different color for this, if I put 2 on this number line and negative 2, negative 3 is less than negative 2. However, 2 is less than 3. We have a reflection, a flip, if you would. All right. So if we divide or multiply by a negative, if that is introduced here, then something changes. So for part A, divide by 3, x is less than 2. And that's it. No change, nothing crazy. We just divided by a positive number. So in interval notation, that would be negative infinity to 2, not including 2. Part B, we will add 1 to both sides. Greater than or equal to 6, dividing by negative 2, which means x is less than or equal to 3, or something missing there. Negative. All right, then x is less than or equal to negative 3. Writing that in interval notation would be negative infinity to negative 3, including negative 3. All right, part C, we'll subtract 5. So negative x is greater than positive 5, dividing by negative 1. X is less than negative 5. So writing that in interval notation, we'd have negative infinity, comma negative 5, not including negative 5. All right, example 5, solve the inequality. Again, just like equations, as long as we don't divide or multiply by a negative. In that case, something changes. I'm going to go ahead and add 7x to both sides. Now the reason I'm doing that is because things change when I have a negative coefficient on x. By doing this, I have a positive coefficient on x. So 17x minus 4, and that is greater than or equal to 13. Now we can add 4 to both sides. So 17 is greater than or equal to 17x. Dividing by 17, I have 1 is greater than or equal to x, also known as x is less than or equal to 1. Right, so I can write that in interval notation as negative infinity to 1, including 1. Number 6, solve the following inequality. Write the answer in interval notation. I can do just like with my rational equations that we saw in the last section. I can clear fractions here. Okay, I'm going to multiply everything here. Now I'm going to multiply by a positive number. That way my interval or my inequality does not change. In this case, the least common multiple of 4, 8, and 3 is going to be 24. So I'm going to multiply both sides. In fact, let's write that a little differently. Let's just say this side by 24 and, well, this side by 24. Just to make the notation a little bit more accurate. All right, so on the left side, that is negative 72. Negative 72 over 4x is greater than or equal to, that'll be negative 120 over 8 x, nope, no x there, plus 48 over 3x. Now the point here is that these all reduce, so this is negative 18x is greater than or equal to negative 15 plus 16x. I'm going to add 18x to both sides. So what I get is 0 is greater than or equal to negative 15 plus 34x. Okay, now adding 15 to both sides. Okay, I get 15 is greater than or equal to 34x, and one more step, divide by 34. 15 34ths is greater than or equal to x, or x is less than or equal to 15 34ths. So writing this in interval notation, negative infinity to 15 34ths, including 15 34ths. All right, number 7, solve the compound inequality. Now there is a meaning here of a compound inequality that we should probably discuss. What this means is that 3 is less than or equal to 2x plus 2, and 2x plus 2 is less than 6. This is shorthand. Okay. This, right here, is shorthand for saying this is true and this is true. So a common tactic, and what I might suggest you do for a while, is separate the two and solve them separately. Now we might be able to put them back together in the end, depending on how this turns out. For the first, we'll subtract 2. So 1 is less than or equal to 2x, which means that x, or that 1/2, is less than or equal to x. And subtracting 2, if you notice we're doing the same moves here. 2x is less than 4, x is less than 2. 1/2 is less than or equal to x, and x is less than 2, which means we could write this as 1/2 is less than or equal to x is less than 2. We could write that all together in that way. Okay, now the potential shortcut here. Okay, there it is, and probably want to write that in interval notation as well. I could have just worked with it the way it was. Okay, so 3 is less than or equal to 2x plus 2 is less than 6. I could have subtracted 2 from all three sides. Okay, by doing that, I get 1 is less than or equal to 2x is less than 4, and then I divide by 2, giving me 1/2 is less than or equal to x is less than 2. Now you see we ended up with the same solution in both ways. Okay, so the way that you do it does not matter. However, I do suggest the first way I do this, at least for a while. Now to write this in interval notation, let's go ahead and write this. It's between the left endpoint is 1/2. The right endpoint is 2. 1/2 is included. 2 is not. All right, number 8. We have a 3-part inequality again. I'm going to break this up into 3, or into 2 different inequalities. So the first is 3 plus x is greater than 7x minus 2, and 7x minus 2 is greater than 5x minus 10. All right, on the left, I'm going to subtract x from both sides. So 3 is greater than 6x minus 2, adding 2 to both sides. 5 is greater than 6x, and so 5/6 is greater than x, or x is less than 5/6. And okay, over here on the right, I'm going to subtract 5x from both sides. All right, so I get 2x minus 2 is greater than negative 10. Adding 2 to both sides. 2x is greater than negative 8, or x is greater than negative 4. All right. So x is less than 5/6, and x is greater than negative 4. The left endpoint in this would be negative 4. And the right endpoint would be 5, 6. And neither of those are included. All right, number 9. Describe all values x within a distance of 4 from the number 5. Okay, what this means and how I'm going to write this symbolically. Well, the absolute value is the distance from a number to 0. If I just say the absolute value of x. So if I wrote the absolute value of x minus 0, that's how far x is from 0. So if I want to know how far it is from the number 5, let's just do this. The absolute value of x minus 5. Now the distance is 4. So it's within a distance of 4. That would be less than or equal to 4. Okay? So now that we've got that out of the way, I'm going to scratch this and write absolute value of x minus 5. Now the way we want to interpret this, and this is going to be a general rule that I'm going to write, okay, the absolute value of x is less than a number k, means that negative k is less than x and it's less than k. Okay, this is the rule. Hold on to that. Okay, so how I'm going to write this then is negative 4 is less than x minus 5, and that's less than 4. So solving this, I'm going to add 5 to all 3 sides, which leads me to 1 is less than x is less than 9. Or less than or equal to. I left off my equal to there. All right, so in interval notation, that is 1, comma 9, brackets on both ends. Now let me just draw a number line to illustrate this point. Here is the number 5. Here's the number 9. Here's the number 1. How far is 1 from 5? It's a distance of 4. How far is 9 from 5? A distance of 4. So all of the numbers between 1 and 9, the numbers between 1 and 9 are within a distance of 4 from number 5. All right. So example number 10, absolute value of x minus 1 is less than or equal to 3. Okay, this is actually trying to figure out what numbers are within a distance of 3 from 1. Okay, now we'll go ahead and write that as an inequality. Based on that rule we just stated, negative 3 is less than or equal to x minus 1 is less than or equal to 3. Adding 1 to all of these gives us negative 2 is less than or equal to x is less than or equal to 4. Or in interval notation, negative 2, 4, and those are both included. And again, if I draw my number line with 1 at the center, okay, and I go out a distance of 3 in either direction. So I add 3 and I subtract 3. I get 4 and negative 2. And that is the interval that I just described. All right, number 11. Given the equation y equals negative 1/2 absolute value of 4x minus 5 quantity plus 3, determine the x values for which the y values are negative. All right, so what this is actually asking us to find is when is negative 1/2 absolute value 4x minus 5 plus 3, when is this less than 0? Which will bring us to a new rule in just a moment. Let's isolate our absolute value. We'll subtract 3 first. All right, so negative 1/2 absolute value 4x minus 5 is less than negative 3. Now we will multiply by negative 2, which will flip our sign so that we have absolute value of 4x minus 5 is greater than positive 6. Now we have a greater than here. So here is the rule for that. Absolute value of x being greater than k means one of two things. Either x is less than negative k, or x is greater than k. Again, there is our rule. Hold on to that. So I'm going to take this expression and convert it into two inequalities. I'm going to write them here below. All right. 4x minus 5 is less than negative 6, or 4x minus 5 is greater than 6. All right, solving the first of those, adding 5 I'm going to transition up here. Now, I'll finish this out here. For both of these, I'm going to add 5 to both sides of that. So for this one, 4x is less than negative 1, or 4x is greater than 11. So x is less than negative 1/4, or x is greater than 11/4. So to write this in inequality form, we have that. To put this in interval notation, we have negative infinity to negative 1/4, not including negative 1/4. We've also got our separate interval, 11/4 to infinity, and then we will union those two. That's how we'll write that. All right, that is the end of this section on linear inequalities and absolute value inequalities. Now, I do want to make the point, do not forget these two things. In fact, write them down and refer to them. Write them down and refer to them. All right, that's it.